Hello everyone, my name is Shreyans Contetta, and together with my friends Michael Gillette and Jonathan Rohr, we have created TutTut, the IoT rainfall detector, for our capstone project. We've made considerable progress on TutTut since last term when we last did a video, and we're excited to tell you what that progress is. But before we can do that, we obviously have to give you a recap of what our project is. Now, TutTut, the Internet of Things raindrop detector, is a project that's under the domain of the OPENS lab here at Oregon State. OPENS meaning, of course, openly published environment sensing. Now, what TutTut can do is that it can detect a raindrop of any size, and then it can get an idea of that raindrop mass from the intensity at which it's falling, and then using those metrics, it can even detect the frequency of the raindrops to a timer we have set up. Now, after TutTut gathers all this information, it'll be able to wirelessly transmit all that to a central server and then store it inside of a database. So what is the purpose of TutTut though? Like, what can this actually do when it's being made? Why does anybody need this? So, when it starts to rain, TutTut will begin recording the force that's being exerted on our MEMS sensor by each individual drop, using a scale within the range of 0 to 100. A reading of 0 means that no rain was detected whatsoever. A reading of 100 means an absolutely insane amount of rain was detected, an absolutely cataclysmic amount. Now, with this scale, we can provide a key with ranges that will show what these given readings might mean. So 0 to 15 would probably represent a mist or barely raining at all. 15 to 30 would represent light rain. You might want to wear a jacket. 30 to 45 would represent a medium rain, so you might want to wear an umbrella. Now, TutTut will also clock the time between raindrops, and it will provide an average for both of these metrics after you get about 100 readings. This is quite useful, as farmers can put this into their crops and into their fields and get a decent idea of how much rain is falling and know how much water they have to give their farms. This will help, obviously, massively with water conservation. So what is our current progress so far? Well, I will be talking about the progress that we've made on the microcontroller side of things. We chose the MEMS sensor as opposed to other sensors like the accelerometer or the piezo transducer because it's much more sensitive. The MEMS sensor can detect the forces of impacts, and we have code that will give us the average amplitude for a specific duration of time. Now, this specific duration of time is used to calculate the frequency that raindrops impact the sensing area. Our microcontroller enters low power mode when the sensor hasn't detected a drop in 1 minute. A drop hitting the sensing area will trigger an interrupt that will wake up the microcontroller so that data can be gathered again.
Hello, this is Michael Gillette here to take over for Shrey on our current progress. So, in the Opens Lab, we were using the 3D printer, one of them, they have many, on site to print the disks and other components that we were going to use in our project. So first we made some 3D prints of disks to print off and test using our sensor. All of these components were created using a software called Autodesk Fusion 360. We originally tried to make this in AutoCAD architecture, and that proved to be extremely difficult. We couldn't even figure out how to make a single disk successfully. So once we made those models in Fusion 360, which was much easier, we learned how to use Autodesk NetFab, which is a website you can upload your Fusion 360 meshes to, and it will check to make sure that there are no errors in it. We got our fixed file from the website, and then we used the program Kira Lolsbot to compile our meshes into a file that would be recognizable by the 3D printer. The SD card was then taken out and put into the Opens Labs TAS 3D printer, and we select our project from the interface and begin printing the designs. Each of these prints takes many hours, and so we usually had to start the print, wait around 15 minutes for it to get going, and then just leave and hope that they printed out the way we wanted them to. So some problems we encountered were fairly typical ones. We had to learn a lot of new software and technologies in order to do this project properly. We had to learn Fusion 360, NetFab, and the Kira Lulzbot software to make this possible. We also encountered the problem of time constraints, where all of us were students and all of us had jobs, so sometimes finding the time to get together to work would be a difficult task. In addition, we sometimes also had some difficulty linking up with our client, Chet Udell. He's a very busy man, and he cannot make every meeting. We originally scheduled weekly meetings every Thursday with Chet, but we've only been able to make, or he's been only able to make about 2 or 3 of them. What is left to do is that we plan on maybe printing another model of our casing to experiment with. So our original casing has a flat sensing area, and we were hoping to print one that had a 30 to 45 degree angle so that the water wouldn't accumulate on top and would instead run off. We want to try the angled model. Yeah. So after we do that, we need to finish setting up our microcontroller to send the data it collects to our designated Google Sheets using the Pushing Box API. We have the information of how to implement it, but we just need to finish that up. This Pushing Box API tool allows us to upload data to the specified document, which in this case is a Google Sheets document, in real time, so that we can record and review the results as they are happening. The last thing we need to do besides those two is that we need to make adjustments as necessary to the casing that we have printed out to make sure that it's waterproof so that the electrical components within are not affected.
Hey guys, my name's Jonathan. I'll be taking over from Michael. I'll be talking about the code that we have so far. Last slide we mentioned we have to finish the Pushing Box API stuff, the sending of our data to a Google Sheets. We do have a base structure of how that is, and a lot of the code is provided to us by the Opens Lab. So I did get it to kind of start working, but we do need to test it more thoroughly to make sure that it is foolproof. So to begin, in our main loop, we make an OSC bundle, which is part of a library that is provided to us along with a lot of these other functions. The Opens Lab has a huge network of libraries already. So basically this bundle that we create just is like a housing for information as we send it to different functions. So we then call our gather data function that I will be talking about in a later slide. This is where all our data collection happens, and after all our data gets collected, we append these key values to the bundle we created up above. So essentially average, frequency, intensity, those are basically the headers of the columns, and then average and frequency are the values that are attached to the header right next to it. So those get appended to the bundle, and then the bundle gets logged, which this function basically tells it to send it to some Pushing Box code that creates a URL using these values, and then that URL gets sent as a GET request to Google Sheets. And then Google Sheets, on that side we have a script that will interpolate the URL and create a Google Sheets with our data. So here's our gather data function. First we create a sensor vals array. This will hold all our values that we'll be gathering. And then this code right here in this if statement is for our sleep function, because we want our device to go to sleep when it's not raining. It doesn't work 100% right now. It does have some bugs, but essentially we want it to detect when it's not raining. Then raining will be false, so it will go into this statement. It will attach an interrupt on the sensor pin. It will go to sleep, and then when that sensor ping, when the interrupt gets triggered, then it will wake up, and raining will be sent back to true, and it'll go into this else if statement, which the first thing we do in this if statement is to create a reference time for our timer that we'll be using. So this is the function that we'll be using for our timer. It's called a call timer. You put in a start value and a duration, and it takes those and with a reference time creates a start time and end time, and while timer is between those times, then it returns true, which means the timer is going. And when it suppresses the end time, then it returns false, which means the timer is ended. So immediately after that else if from 2 slides ago, we have a do while loop, and in this if statement we call the call timer function, and if it is true, then that means the timer is going. So we start reading from the pin. So we take a reading, we do a conversion to put it into a decimal form, and then if it's greater than the threshold that we set, it will place the value into the sensor vals array, it will increment I, and then this function, this if statement will loop as long as loop reset equals false. And as long as call timer is true. So then if call timer is false, which means the timer is ended, then it goes into this else if statement, which adds up all the values in the sensor vals array, divides it by the number of values there were, which gives us our average, and then to get our frequency, we have you take the number of values that were in the array divided by the duration, which is the same duration we've been using for our call timer, which in our final project will be 2 minutes. And then we have a switch statement for our intensity value, which will essentially take our average and see if it fits in these separate ranges, and says if it's light rain, medium rain, or heavy rain, and we can add more intensities. As we go. And then at the end it sets loop reset to true, which tells our code to go back into the main loop, log the data, and then that loops, which will call this again and reset the timer so we can get a whole another 2 minutes of data. And then we have our prototype here. On the left is our 3D printed enclosure. It's just a prototype. It's very rough, but it holds everything. The sensor is on this disk underneath it, so water will hit this disk and the sensor will send the data through these wires, through the breadboard, and our feather MO will be attached to a battery, so it will be able to be powered up while in the field. And this bottom is removable, so we can configure it while it's inside. So our next step is to make sure we can make this watertight, because it is going to be out in the rain, it's going to be out in the nature, so we want to make sure that environmental the environment can't affect it in negative ways. So that's what we're going to be doing a lot of spring term, is fixing bugs and making sure that this enclosure can actually be used in the field. And that's our project.